In this video, we will talk about derivatives. So, first of all, suppose we are given this graph of a parabola, and this pink line is what's called the tangent line at x equals 1, and we want to know the equation for this tangent line, when we only know the equation for this parabola. Well, to find an equation of a line, we need to know what the slope is. So the slope is the rise divided by the run. However, we only know one value, 1, 1. If we want to compute the slope, we would need a second point on this line, but we don't know that point because we don't have an equation for it. But it's still possible to find the slope by approximating this. So let's say we have another point A, then the height is given by a squared. So this is the point A and A squared, and we can draw a line connecting these 2 points. Now this blue line is not this pink line, but it's kind of close to it. So what is the slope of this blue line? The slope of this blue line is going to be the rise, which is a squared minus 1, divided by a minus 1. So a squared minus 1 divided by a minus 1 is the slope. Now we can approximate the pink line better if we choose a point, let's say a prime, that's even closer to 1 than a, right? So this orange line, the slope becomes closer and closer to the pink line. So if we figure out what the slope is as a approaches this point, it'll be the slope of the pink line. And we've discussed how to compute things when some quantity is approaching something, and that's the limit. We know how to compute this limit. We just factor the numerator. These will cancel out in the limit, and we plug in 1. So this is 2. So the slope of the pink line is 2, and it crosses this point 1, 1. So the equation of the pink line is given by something like this. Now let's consider a little bit more abstract setting. Given some unknown function f of x, can we compute the slope of the tangent line at some point A? Well, let's repeat the same process. Let's pick some point that's kind of close to A. Let's call that x. And we form the line that connects this point, a and f of a, to this point, x and f of x. Then the slope of the blue line is this difference, f of x minus f of a, divided by this difference, x minus a. And the idea was to let x approach a. And so this will give us the slope of the tangent line at a. And the notation that we'll use is f prime of a, or df over dx of a. Although this is not really a fraction, it's just a notation. And we'll call f prime the derivative of f at a. If we let x equal a plus h, then we can rewrite this as the limit as h goes to 0 of f of a plus h minus f of a divided by h. And this gives us another formula for the derivative that's useful sometimes. So let's do a quick example. If f of x is x squared, then what's f prime of a? This is going to be the limit as x goes to a of f of x minus f of a divided by x minus a, which is the limit as x goes to a of x squared minus a squared divided by x minus a. We can factor the numerator. These will cancel, so we end up with 2a. So f prime of a is 2a. Or if you write it as a function of x, f prime of x is 2x. An important concept to keep in mind is that the derivative is the instantaneous rate of change. So what does it mean to be the instantaneous rate of change? Well, let's look at one example. Suppose we have a function that gives the height of a rocket at time t. Then we can ask the question, what is the velocity of the rocket at time t? So how fast is it moving? Well, we need to be a little bit more precise when we say velocity, because velocity is the displacement divided by the time. But what do we mean by the displacement at a single moment in time t? To compute this, you would need some elapsed time. So when we ask for the velocity of the rocket at a specific time t, what we really mean is we want the instantaneous velocity, or the instantaneous rate of change of the position of the rocket. But we just developed the right thing that will compute such a quantity, That is the derivative of the height or the position.